Welcome back, dear students. So, today I'll be doing the fifth lecture on quantum theory. So, yesterday I had done up till this Einstein's concept of black body radiation. Then for these relativistic particles, when a particle travels with the speed of light, its mass changes, and this is called as the m is equal to m0 by square root of 1 minus v square by c square. This is the relation now the mass changes. Okay, where m0 is the rest mass of the body. Now, according to Einstein's special theory of relativity, according to Einstein's special theory of relativity, what happens? The mass of a particle can be converted into equivalent energy given by delta E is equal to delta M into C square. Okay, this is known as the mass energy. This is known as the mass energy equivalence relation. Okay. This is known as the mass energy equivalent relation, and for a relativistic particle, what is a relativistic particle? Relativistic particle is a particle moving with the velocity comparable to the velocity of light. The total energy E is given as square root of p square c square plus m0 square c to the power 4. Oh, sorry. It's given by p square c square plus m0 c square, actually m0 c square. Okay, where this m0 c square is called as the rest mass energy. m0 c square is called as the rest mass energy. Okay, m0 c square is called as the rest mass energy. Okay, so now let's come to the next topic. What is the next topic? The next topic is called as the Compton effect. Okay, so what is this Compton effect? Okay, so up till now, what did I tell about quantum mechanics? Quantum mechanics is that it is for first of all, it is for microscopic objects. Okay, it's not for actually macroscopic objects. For macroscopic objects, the mechanics which describe the motion is your classical mechanics. Okay, but for microscopic particles, it is described by the quantum mechanics, and those particles move with the velocity of light. Okay, then you have that light. Okay, light has got dual nature. Okay, light has got dual nature. This is a very important this is a very important point of quantum mechanics, that light has got dual nature. Dual nature means it can behave as a particle in some phenomena. Okay, it can behave as a wave in some other phenomena. Okay, it is behave as a particle, it can behave as a wave. So it can simultaneously behave, no, not simultaneously, in some experiments it can behave as a particle, in some experiments it can behave as a wave. Now this was not before the advent of quantum mechanics, this was not proved. Okay, so in some experiments it can behave as wave, in some experiments it can behave as particle. So this was not proved before the advent of quantum mechanics. What are the experiments? Wave. In which experiments is behave as wave? See, these are important things. You can be asked these kind of questions. You have got what experiment you have got? Planck's constant. Planck's constant experiment you have got in your laboratory. So there you can be asked these kind of questions. Okay, so wave in which experiments it behaves as wave, which you have studied already. Interference, diffraction, polarization. Interference, diffraction and polarization, in these three experiments it behaves as a wave. Where it behaves as a particle, it behaves as a particle in which experiments? It behaves as a particle in the experiments. Now comes this thing, the black body radiation. Okay, then photoelectric effect. That Planck's constant experiment is basically the photoelectric effect only. Then comes your Compton effect. Now this Compton effect. So in other words, the Compton effect proves that light can behave as a particle also. Compton effect proves that light can behave as a particle also. So how will you prove that light can behave as a particle? Okay, so in the year of 1922, okay, Arthur Holly Compton, okay, discovered the Compton effect. Arthur Holly Compton discovered the Compton effect. In the year 1922, Arthur Holly Compton discovered the Compton effect. Okay, so what happens in the Compton effect actually? Okay, what happens in the Compton effect? So in the Compton effect, actually what happens is that high energetic X-rays, okay, high energetic X-rays, okay, X-rays are of wavelength very small, that is energy is very high, 1.54 angstrom, like that energy is the wavelength of X-rays. Okay, high energetic X-rays are incident on basically a carbon atom, on a actually graphite block. High energy X-rays are incident on a graphite block. Okay, high energy X-rays are incident on a graphite block. Then after the incidents, what happens? After the incidents, after the incidence, okay, the X-rays which are scattered, okay, have got X-rays which are scattered have got lesser wavelength than the incident X-ray. So here lies again a discrepancy. That what happens, that I mean, there is a wavelength difference between the incident ray and the scattered ray. Now, I mean, if you go by the classical theory, okay, মানে if you consider the classical electromagnetic theory, if you consider the classical electromagnetic theory, this cannot be explained. If you consider the classical electromagnetic theory, this cannot be explained. Okay, this cannot be explained. So there is a discrepancy. Why this cannot be explained? Because according to the classical electromagnetic theory, suppose this is an X-ray. Okay, it is colliding with the graphite block. So there are say electrons here. There are electrons like this. Okay, so when the graphite block is colliding, now there are the outermost electron. The outermost electron, it will definitely, I mean, it will be easier to take it out. Okay, so what will happen actually? What will happen? So when the X-ray is hitting the graphite block, these electrons will start oscillating, right? These electrons will start oscillating. Now with the energy of the X-rays. Now when they will oscillate, they will emit radiation, right? They will emit radiation in all directions like this. With what energy? Now these electrons will start oscillating with the energy of the X-ray only. Now when they will oscillate, so they will emit that energy only, which was the energy of the X-ray, or that frequency only. If this is lambda, then this will be lambda only. That is only the classical electromagnetic theory. Okay, when the photon of wavelength lambda hits a target, this is a graphite block, so there are electrons here. Now that is the outermost electron. They will again, it will absorb, just like that laser, the electrons will absorb the energy, and they will start vibrating, and and oscillating. Now when they are oscillating, just like black body cavity only, when they will start oscillate, they will emit radiation. They will emit radiation of the same wavelength. But no, here this doesn't happen. Here this doesn't happen. Okay, so what actually Compton then assumed that you cannot take it as a you cannot consider the yeah, as a wave. Okay, you cannot consider the X-ray as a wave. You consider it as a particle. Okay, if you consider this as a particle, then you can explain this. Okay, I mean, if you consider this as a billiard experiment, so if you the result of the Compton effect, could be explained if the uh, X-ray is considered as a stream of particles, that is photon, instead of a wave. Okay, so it is similar to a billiard game. Okay, billiard game. How it is similar to billiard game? That is this is the diagram. Suppose this is one extranuclear electron. This is one electron. Okay, and say this is a photon like this. This is a photon like this. Photon of, this is the incident photon. This is the incident photon. Okay, having energy is equal to h nu. Now when this will collide, suppose consider it as a billiard experiment, but this is also one, this photon is also one billiard ball, the electron is also one billiard ball. So what will happen? They will scatter, electron will scatter in one direction, right? I mean electron will scatter in one direction like this. This is the electron and this is the photon particle here, like this. Okay, just like billiard ball experiment. What happens when you hit one ball with another ball? So the balls scatter in different directions. This is a elastic collision. Okay, elastic collision of two particles. So this is basically the elastic collision of two particles. Elastic collision of two particles. Elastic collision of two particles. Okay, now another thing I want to remind you that why did this Mr. Compton use X-ray? Why not your visible light? Why not visible light? The reason is very simple, that visible light wavelength is very high. That is, its energy is much lesser than that of X-ray. X-ray, its wavelength is very small and its energy will be definitely, its frequency will be very high, so its energy will be very high. So I mean, what is basically needed here? I mean, now in this Compton effect, means when this scattering will take place, you need a real collision. Okay, that electron will also scatter and the photon will also scatter. How can this happen? Means when the incident radiation is a very high energy, then it can collide with the which electron? Now this is the outermost electron. This is actually the outermost electron of the orbit. Okay, not the inner electron, not the the electron which is nearer to the nucleus. This is the outermost electron. So when now if suppose instead of X-ray this was what to say, the visible light, if instead of X-ray it was visible light, then its energy is very less, so it cannot really collide with real energy. Nothing will happen to the outermost electron. Okay, it will remain there only. Okay, so but if it has got X-ray, the X-ray has got high energy, so with this high energy it can collide and take out, the binding energy of the outermost electron is very less compared to the innermost electron, so it can take out the electron. this collision, genuine collision can take place. Okay, genuine collision can take place. So that is why you are using visible light. Sorry, X-ray. So this is the scattered photon. Okay, this is the scattered photon. Okay, and this angle is called the theta. This is the angle of scattering. This is called the angle of scattering, and this angle is phi. This is called as the angle of recoil. This is called the angle of scattering, and this is called as the angle of recoil. Okay, so now if you basically now if you consider it as a particle, then you can explain this. That is definitely, I mean, when there is a collision between particles, this is a particle and this is a particle, then definitely the energy of the scattered particle will be lesser than that of the incident particle. Okay, so suppose if you, I mean, like if you the collision between two persons also. Okay, suppose you're playing football and you are running very fast. Okay, but then there is a collision, another player commits a foul, so when there is a collision, your energy get decreased. So similarly, when there is a collision between the billiard balls, the the energy with which the ball is incident with another ball, so after collision what happens? Definitely its energy will decrease because it loses energy in the collision. So if you can describe in terms of particle, then you can describe the ultimate result. Okay, so now we'll basically now do mathematics and calculate the different in this wavelength. Now suppose the wavelength, this is nu, that is its wavelength is say lambda, and wavelength of the scattered photon is say lambda prime. So we'll now calculate basically lambda prime minus lambda. What is lambda prime minus lambda? We'll do that. Okay, so you have to apply the all this equation of conservation of energy and conservation of momentum. Okay. Okay, so kinetic energy of the electron, kinetic energy of the electron after collision, kinetic energy of the electron after collision is equal to what? Is equal to before the collision. What it was before the collision? It was its rest mass energy, because the electron is at rest. Okay, what is the rest mass energy of the electron? So this is relativistic. At rest, what is the rest mass energy? m0 c square. I had done in the last class, that is here. This is m0 c square. The rest mass energy of any particle is m0 c square. Here m0 c square, where m0 is the rest mass of the electron. Okay, so after say after collision, the energy after here is say mc square. Okay, so where m is equal to m naught by square root of 1 minus v square by c square. Okay, so total kinetic energy after collision is mc square minus m naught c square. Okay, so this is the thing. Acha, now according to by the law of conservation, of energy, according to the law of conservation of energy, what is the before collision, what is the entire energy of the system? That is, energy of the photon is h nu, okay, plus energy of the electron is m naught c square, rest mass energy. So this will be equal to, after collision, what is the frequency? This is lambda prime. Lambda prime is the wavelength, frequency is say nu prime. So h nu prime is the energy of the scattered photon, h nu prime plus what is the energy after collision of the electron, that is mc square. Okay, so let it be equation 1. This is the by the law of conservation of energy. Okay, so now by the law of conservation of momentum, by the law of conservation of momentum, by the law of conservation of momentum. Okay, now this energy is a scalar quantity. Okay, so you should be concerned only with the magnitude, not the what to say, not the on which direction. Now by the law of conservation of momentum is not, momentum is a vector quantity. So in momentum we will have two components, means one along the direction, along this direction, that is along the direction of the incident photon, and perpendicular to the direction, that is this direction. Okay, so so by the law of conservation of momentum, okay, so first let us take along the direction of this, that is along the direction of the incident photon. So what is that? So momentum of the electron, that is before collision, the incident photon energy is h nu. So what will be the momentum? H nu by c will be the momentum, h nu by c, plus momentum of the electron is what? It is at rest, there is no momentum, so 0 is equal to what will be it? H nu prime by c will be the momentum of the scattered photon and its component along the direction of the incident photon, that is h nu by c into cos theta, plus the momentum of the electron, what will it? It's m, say, and its velocity is say v, so mv into this angle, this is called angle of recoil, so this mv cos phi. Okay, so let this be equation number 2. Okay, acha, now perpendicular to the direction of the incident photon, this is along this. So along this, before collision, do you have any component? This photon is moving in this direction, so it doesn't have any component here, that is, I mean, cos 90 degrees, so 0. So electron is already at rest, so no here. So here it will be on the left hand side, it will be 0, and this will be h nu prime by c into sine theta, plus this will be mv into sine phi. So let this be equation number 3. This be equation number 3. Okay, so now equation number 3. Okay, so now how can we now let us modify this equation like this. This will be h nu by c is equal to h nu prime by c into cos theta plus m. So what is m? M you can write is like this, m is equal to m naught by square root of 1 minus v square by c square. Okay, so so this will be h nu I mean v by c here, v square by c square, that is v by c is taken as beta. Okay, so v will be beta into c. Okay, so from here what will you get? M into v will be here beta into c. So m in this will be m naught by this, so this will be m naught into beta into c by square root of 1 minus beta square. Okay, into this is cos phi, so this is cos phi. Okay, so this is the thing, and this will be again this 0, this one, this equation will be 0 is equal to h nu prime by c into sine theta, plus this will be again m0 beta c by square root of 1 minus beta square into sine phi. Okay, so this will be equation number 4, this will be equation number 5. Okay, so now let's proceed further. Now this will be now 1 2 3 4 and 5. Okay, so what can you do now? Here you have got here this thing, so you can write it like this: h nu by c minus h nu prime by c into cos theta is equal to m naught into beta c by square root of 1 minus beta square into cos phi. Okay, and this will be h nu prime by c into sin theta will be equal to minus m naught beta c by square root of 1 minus beta square into sin phi. Okay, so I mean squaring and adding these two equations. Okay, squaring and adding these two equations, what will you get? If you square and add these two equations, what will you get? You will get here m naught square beta square c square by 1 minus beta square. Okay, and sine square for this, that is 1. So this will be h nu by c minus h nu prime by c cos theta whole square plus h nu prime by c whole square into sine square theta. Okay, so you will get this thing. So this will be actually, if you write it here, if you do it, that will be actually h nu by c whole square plus h nu prime by c whole square minus 2h square nu into nu prime by c square into cos square theta. Okay, this will be the thing. Acha, now let this be equation number 6. Let this be equation number 6. Okay, so now next what will you do? Next here say from this equation, that is from this equation, that is equation number 1. Okay, from equation number 1, what you can write? mc square is equal to h nu minus h nu prime plus m naught c square. Okay, so this will be mc square will be equal to h nu minus h nu prime plus m naught c square. Okay, so you simplify m, rather you expand m naught c square by square root of 1 minus beta square is equal to h nu minus h nu prime plus m naught c square. So now if you square both sides, what will you get? M naught square c to the power 4 by 1 minus beta square is equal to h nu minus h nu prime plus m naught c square whole to the whole square. Okay, whole square. So now if you divide both sides, like here you have got, you have to come here, no, this is c square here. So to make this simpler, instead of c to the power 4 here, you have to bring somewhere c square. So divide both sides by c square. So m naught square c square by 1 minus beta square is equal to what it will be? H nu by c minus h nu prime by c plus c square. So m naught c whole square. Okay, so this will be m naught, this will be what? H nu by c whole square plus h nu prime by c whole square minus 2h square nu into nu prime by c square plus m naught square c square plus 2 m naught into h into nu minus nu prime. Okay, So let this be equation number what this equation, this was equation number 6. Let this be equation number 7. Let this be equation number 7. Okay. Now here this is equation number 7, m naught square c square by 1 minus beta square, and this one is equation number see here m naught square beta square c square. Okay, so let us do, this is beta square here, and denominator is 1 minus beta square. Okay, and here there is just I mean just c square, no beta square. So let us do equation 7 minus equation 6. Equation 7 minus equation 6. If you do, what it will come, m naught square c square by 1 minus beta square into 1 minus beta square. Okay, that will be equal to, see here also there is this thing only, h nu by c square and h nu prime by c whole square, so those will cut ultimately, and what will you get here, this will cut, and ultimately you will get m naught square, this c square, this thing, this will cut here. Okay, this will be left, m naught square c square minus 2h square nu into nu prime by c square. Okay, and there will 1 minus cos theta, okay, plus 2 m naught h into this nu minus nu prime, this thing will remain. Okay, so what will you get here, this 1 minus beta square will cancel, so what will you get here, m naught, so this m naught square will cancel, so you will get 2 m naught into h into nu minus nu prime will be equal to 2 h square nu into nu prime by c square into 1 minus cos theta. Okay, into 1 minus cos theta. So now just these are simplification now. So m naught into h into c. Okay, just you multiply, you take one c here and keep c here, and you divide both sides by I mean nu prime, you divide both sides by nu prime. So what will you get, 2 h square here there is 2, here there is 2, the 2 will cancel, so and here h square, there is h, so h square by c into 1 minus cos theta. Okay, so now this will be so this will be c into, this will be 1 by nu prime minus 1 by nu is equal to h by m naught okay, h by m naught c into 1 minus cos theta. Okay, so this will be c by nu minus c by nu prime minus c by nu. What will be that? C by nu prime minus that will be lambda prime minus lambda. This will be equal to h by m naught c into 1 minus cos theta. So this will be delta lambda will be equal to h by m naught c into 1 minus cos theta. Okay, so this will be lambda c into 1 minus cos theta. Okay, where lambda c is equal to h by m naught c. Okay, lambda c is equal to h by m naught c, and lambda c is called as the Compton wavelength. Lambda c is called as the Compton wavelength, which is a universal constant. Okay, which is a universal constant. So delta lambda is equal to lambda c into 1 minus cos theta. So if you do the expand it, 2 sine square theta by 2. Okay, sine square theta by 2. So, and this lambda c is a universal constant. Lambda c is a universal constant, and its value is 2.42 into 10 raised to minus 3 nanometer. Okay, 10 raised to minus 3 nanometer. So you are seeing here that lambda c is a universal constant, and I mean it is constant for a material. Okay, and so wavelength shift is known as this. The delta lambda is called as the wavelength shift. Delta lambda is called as the wavelength shift. Okay, and it is independent of the wavelength of the incident radiation. Okay, it is also independent of the scattering material. Okay, so this is delta lambda is independent of the wavelength of the I mean delta lambda is independent of the wavelength of incident radiation. Delta lambda is independent of the wavelength of incident radiation. Okay, it is also independent of the scattering material. It is also independent of the scattering material. Okay, it is only dependent on theta. What is theta? The theta is the scattering angle. Okay, theta is only dependent on the scattering angle. So this is the thing that there is always a wavelength shift in the Compton effect between the incident radiation and the scattered radiation, and this proves that the light can also behave as a particle in some experiments, and in this Compton effect light behaves as a particle. Okay, so thank you.